going to be a talk about reverse engineering manifolds from error-correcting codes. It's going to be a talk talking about something involving quantum error-correcting codes and systolic geometry. And in the spirit of suggesting questions from last night's talk, if you're a mathematician, you might be wondering, what is a quantum error-correcting code? And if you're a quantum information theorist, you might be wondering, what is systolic geometry? And if you're a physicist, you might want to ask both of these questions. So I'll try to explain all that. And I'll start with actually explaining what is a classical error-correcting code. Classical error-correcting codes, by the way, just to advertise, it's probably like the most important area of 20th century math that you don't really appreciate. You're all carrying devices in your pockets that use quantum error-correcting codes to communicate your cell phones. Classical error-correcting codes to communicate your cell phones. And research in this area has really impacted all of modern society. So classical error-correcting code, let's say there's two people conventionally called Alice and Bob. And Alice has some message, which is just some string of bits that she wants to send to Bob. However, Alice is sending this message over some noisy communication channel, perhaps some radio link or something like that. And there's a chance that as she sends the message, maybe some of the bits will be flipped in this communication channel. Perhaps some of the bits, like a 0, might become a 1 or something. So what she does is she sends it through some encoding map, and out comes some much longer message, so which has some redundancy, which has some extra bits thrown in. And perhaps the channel flips some of these bits in the transmission, but Bob then applies some decoding map and attempts to reconstruct the original message against the noise. The simplest example of this I can give is when Alice uses what's called the repetition code, in which case, if she wants to send a 0, she just sends a string of zeros, say 5 zeros, 1, 2, 4, 5. And if she wants to send a 1, she sends 5 ones, 1, 2, 3, 4, 5. She just repeats herself some number of times. An important property of the code is called the distance. The distance is the minimum number of errors that could occur in the channel in order to convert one valid message into another valid message. So in this case, if 5 times a 0 flipped to a 1, Alice's message of 5 zeros could flip into 5 ones. So in this case, this is distance 5. If that's the minimum number of errors that could occur for Bob to get confused as to what Alice sent and not know that there was any error. If there were half as many, say 3 errors were sent across the channel, it's possible that Alice wanted to send 5 zeros, but instead the last 3 bits flipped. And Bob knows that an error occurred, but he'll get confused and he'll guess, oh, the most likely thing is that Alice was trying to send 5 ones, even though. So if the number of errors is at least half the distance, Bob can get confused as to what Alice was trying to send. Now, formally, you can do much better than this repetition code. And there's an entire field devoted to studying it. But formally, let's define it's conventionally written N, K, D, error-correcting code. And technically, this is an additive error-correcting code that I'll write down. Code will be, so Alice will conventionally, a common way to do this is for Alice's encoding map to be some linear transformation. So is a subspace, a k-dimensional subspace, k-dimensional subspace of f2 to the n. So that is, Alice will send a message that is n bits long, and there's a k-dimensional subspace, which is the valid messages that she'll send, such that the minimum weight, such that, let's say, the minimum over u in the subspace u not equal to 0, the weight of u is equal to d. Here, this weight of u is the Hamming weight. It's the number of ones in it. So in this case, this code that I've written here, this repetition code, is a 5, 1, 5 code. The subspace is the space, spanned by 0, 0, well, spanned just by 1, 1, 1, 1, 1. The all 0 vector is in the subspace, but it's 0. The minimum over u in the subspace that are non-zero is 5. So that's what a classical error-correcting code is. And this k is the number of bits of information that Alice can send through the code. a quantum error correcting code. Let me talk about what a quantum error correcting code is. So I've kind of like, in the classical case, I kind of told a story and then just gave a precise definition in terms of it's a subspace with these properties. So in a quantum error correcting code, I want to do the same thing. I don't want to recap the whole theory of error correction. I'm going to tell a brief story and then give a definition in terms of chain complexes. And actually, to motivate that definition in terms of chain complexes, let me slightly rewrite this classical definition. A convenient way to define this subspace is to impose constraints on the subspace. For example, in this repetition code up here, what we have the constraint is the constraint that if we call these 5 bits B0, B1, B2, B3, B4, then you have the constraint that B0 XOR B1 is 0, B1 XOR B2 is 0, and so on. You have 4 constraints on it. So you've defined this one-dimensional subspace by imposing 4 linear constraints on it. So another way to write it is you could write it as a chain complex, C1 to C0 by some map grad that we'll call a boundary map. And then, C1 will be F2 to the n. And it's also a NKD is a chain complex, such that the minimum over U in H1 of this chain complex, U naught 0, U is D. So this grad, this boundary map from C1 to C0 just enforces the constraint that you're in this subspace. And that's the just an equivalent way to say it. Oh, and K is the dimension of this H1. So a quantum error correcting code should be something to correct quantum information. So you might try to do the same thing. You might try to say, okay, Alice has 2 states that she might want to send, 0 and 1, and perhaps I'll just write 3 repetitions instead of 5. Perhaps what Alice wants to do is apply a map that sends 0 to 0, 0, 0, and 1 to 1, 1, 1. This is a unitary map. So then, acts by linearity. So 0 plus 1 will go to 0, 0, 0 plus 1, 1, 1. This has the advantage then, if in the channel, what happens is some noise, and this 0, 0, 0 state, there's an error, and this gets sent by some error into, say, 1, 0, 0. Bob can detect that an error occurred. He's left the subspace. And the only way for there to be bit flips that Bob won't notice is for 3 errors to occur. This has improved the performance against bit flip errors. However, the channels become more susceptible to phase errors. So if Alice tries to send something like 0 plus 1, which maps to this sum, 0, 0, 0 plus 1, 1, 1, if there occurs a phase error, if what happens is if on any of these 3 qubits there's a phase error which acts as the diagonal matrix, like 1 on the qubit 0, 1 on the state 0 and minus 1 on the state 1, this will cause a phase error, and now there's 3 ways to cause a phase error. So perhaps, I guess, I'm not sure what Peter Shor's motivation was, but he invented the idea of quantum error correcting codes, and I think his realization was, maybe I'm just guessing, we've worsened the performance against phase errors by like a factor of 3 here, but we've improved the performance against bit flip errors by squaring it. You need to have at least 2 bit flip errors to get confused. And so maybe we can do this twice. First, we can encode against something to improve against bit flip and something to improve against phase. So he came up with the idea of having 2 kinds of checks, one to correct bits flips and one to correct phase. So now I'm going to switch notation. I'm going to use Pauli matrices. So for example, this error correcting code here, this classical error correcting code, I'm going to use Pauli matrices, and I'll say that I'll call the qubits 1, 2, and 3. So Z1, Z2 is plus 1, and Z2, Z3 is plus 1. This means we're going to look at the space of states where the first 2 qubits have the same value, and qubits 2 and 3 have the same Z value. It's a constraint that we impose on it. Z1, Z2 equals 1, and Z2, Z3 equals 1, where Z is just the diagonal matrix 1, 1, 0, 0, minus 1. So that constrains you to this subspace. And so we thought, well, let us repeat this thing. We'll have 9 qubits. So we're going to have 9 qubits. We'll have the constraint Z1, Z2 is 1, Z2, Z3 is 1, Z4, Z5 is 1, Z5, Z6 is 1, Z7, Z8. I'm not going to just keep writing the ones, Z8, Z9. And then he had some X checks, X1, X2, X3, X4, X5, X6. What these X checks were is things that acted as effectively to take these logical qubits, these encoded qubits, and impose then an X repetition code on them, and X4, X5, X6, X7, X8, X9, and this is the first error correcting code, quantum error correcting code. This is an error correcting code that has 9, it's an N, K, D, and conventionally people write 2 brackets to denote a quantum one, where it's 9, 1, and it's a distance 3 code. And you can do much better than this, but this was the start of it. So formally, what it gets defined by, again, is a chain complex. And N, K, D quantum error correcting code. And technically, I should say CSS, because this is a particular type of quantum error correcting code. Quantum error correcting code is a chain complex. C2 to C1 to C0 with some maps, grad and grad prime, where all these are over F2, and this thing will be F2 to the n. This middle dimensional thing will be the number of qubits. And these two, grad and grad prime, will encode, grad will encode the z constraints, and grad prime will encode the x constraints. And the constraints have to commute with each other. You can't impose a constraint that like z1 is 1 and x1 is 1. Those constraints don't commute and they can't be simultaneously imposed. And that requirement of commutativity of the constraints is expressed completely in these terms by the requirement that grad prime of grad is 0, that this is a chain complex. So it's a chain complex. The number of qubits is the dimension of this C1, the middle vector space. The number of logical qubits is the dimension of this first homology. And then the distance, well, the distance, there's actually two distances. So the distance is the minimum of what we'll call dx and dz, distance against x and z errors, where dx is the minimum over u in first homology, u0, the weight of u, and dz is the minimum over u in first cohomology, u0, weight of u. So where did this homology and cohomology come in? What we're interested in is something that will say what pattern of z errors could occur that won't violate any x checks. So that will tell us that its boundary has to be 0 because it won't violate any of the x checks. But then also, it can't be one of those z constraints we already imposed. If we go back up to that error correcting code up here, and we have this, say, z1, z2 equals 1, if an error z1 and z2 occur, that's not actually an error. It's just one of the constraints on the code. So even though there's this weight 2 thing that's undetectable, you don't care because you're in the subspace where that weight 2 thing is just a scalar. So you want to mod out by those. And so, well, I'm just telling the story, but this is formally what a quantum error correcting code is. It's this chain complex with these properties. There's a final definition I should make. It is LDPC, standing for low density parity check, if grad and grad prime are O of 1, row and column sparse. Row and column sparse. O of 1 meaning we implicitly have in mind a whole family of these codes where n, k, and d scale in particular ways. And what we would like is that in this family, these matrices, grad and grad prime, both have O of 1 entries in every row and every column. Yes?
I'm not sure. Are you implementing the x and z checks as a maps from Sn, F2 to the n?
Yeah, so the grad and the grad prime encode the x and the x and the z checks. Grad and grad prime encode the x and z checks. It's just in the same way as in the classical error correcting code, grad encodes the checks that were present. So in grad prime, the columns correspond to qubits, and the rows correspond to I guess, z checks. I think with the convention I have here, maybe I have it the other way around. I'm confused which one I'm calling x and z. And then there's an entry if a particular qubit participates in a particular check. And the same way grad, the rows correspond to qubits and the columns correspond to checks. And again, there's a 1 if a qubit corresponds to it is in a particular check. So those matrices encode the checks. So this row and column sparse is another way to say every check involves only a few qubits, and every qubit is in only a few checks. Yes?
I think I missed what H and H prime are.
Oh, homology and cohomology. H1 is, it's the vectors that are in the kernel, the kernel of this grad prime. So the vectors who's, killed by this grad prime, modulo the ones that are in the image of grad. So the ones that are, which is to say, so these are the ones that the x checks don't see, but then ignoring the ones that are already z checks that we've imposed. And then conversely, H1 is the vectors that are in the kernel of the transpose of grad. So the ones whose, if you don't violate any of the checks, the other kind of checks, modulo the ones that are in the image of the transpose of grad prime. Like that. So the homology and the cohomology of this. Yeah, so it's just a fancy way to say, the ones that don't violate any of the x checks modulo the ones that are in the z checks. Yeah. And H1 is just everything reversed, like reverse all the direction of the maps. Okay, so there's been an enormous amount of work in building LDPC error correcting codes with various useful properties. And if you ever want to read the literature, N, K, and D are definitely not the only properties you care about. You care about things like spatial locality, efficient encoding and decoding maps, stuff like that. But for this talk, we'll just worry about N, K, and D. One way of doing it, an extremely fruitful way of doing it, is to draw some inspiration from topology. So if you take any, say, two-dimensional manifold, like a torus, and then you just draw some cellulation on it. So all right, I'm just going to draw a picture, right? And you can identify, say, the top and bottom, right? And then identify also the left and right. So this is a torus. I could draw a better torus. I'm drawing as a plane and identify the left and right. I could also imagine, drawing, oops, sorry, my tablet's sliding here. You could also, all right, so we could say draw a torus. And then on it, you draw some pattern of whatever, draw some pattern on your torus. You draw any cellulation you want, and then every one of these two cells, so a two cell, would be, what you've done is you've divided into little cells, two cells, and then on the boundary of the two cells are these edges, which are one cells, and then there are these vertices, which are zero cells. And what you do is for every one cell, you assign a qubit. For every two cell, you assign an x check, or maybe a z check, I forget my convention. And for every zero cell, you assign a z check. Actually, I think I'm using the opposite convention. So let's say a z check on a two cell and a zero cell is an x check. And this gives you a chain complex. What you do is, so you have one qubit per edge. In this, you have the picture that you've drawn literally tells you the boundary maps. So the boundary map from two cells to one cells is just look at the boundary of this thing. The boundary of this is 4 edges. So this z check acts upon those 4 qubits. It's a product of z, 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 z. It's a product of 4 z's. Similarly, if you want to look at this x check, the so-called co-boundary of this, which is the one cells attached to it, is these 4 ones. And so this x check will act upon these 4 ones here. So every x check also involves 4 qubits in this particular picture I've drawn. You can draw other pictures. So this gives you an error correcting code, the famous toric code. If you do it on a torus, if you make the torus L by L, what you get is you get roughly L squared qubits, actually 2L squared, although you can improve numbers a little bit by twisting things. But if you just do it in the obvious way, it's L by L. And then you have, in every square, you have 2 qubits, one going this way and one going that way. There's 2 logical qubits on a torus. These correspond to just the first homology of the torus being 2. And these correspond to what they are is non-trivial cycles that either go around the torus this way or around the torus this way. And you can immediately see from geometry that the weight of these is at least L. You have to make it all the way around the torus, which takes distance L. 2L squared, 2L code. And then there's also the elements of cohomology, which go on the dual lattice, but those also have distance L. So this is the parameters of this code. You can improve the constants a little bit, and this is an LDPC code, And so D is proportional to square root n in this case. This is the toric code. Toric code is, this was sort of like, it's hard to beat square root n. And for a long time, there was this barrier of like, can you do better than square root n? The first thing that went beyond square root n was Friedman, Meyer, and Luo in, I don't know, around 2000. So they got a code that was square root n, something like log n to the 1/4 or something like that. It's just barely beat square root n. It told you that you could get a quantum error correcting code that was LDPC. If you drop the LDPC requirement, you can get it up to distance n. But if you kept it as LDPC, it was very hard to get above distance square root n. But they showed that you could beat the square root n by a little bit. And so this is important. You know, the log n is not even log n, but a sublinear power of log n was a tiny improvement. It just showed that this was no fundamental barrier. So that's a very important thing, especially psychologically. That, you know, okay, we can beat this. But there was a long time to try to get beyond that. And then there are many advances in 2020 in which it went to square root n, log n, first, I think log n, then log n to the k for any k, then n to the 3/5 over polylog n. So this was the first one that was like really beating n to the 1/2 by more than a polylog. Then, in fact, remarkably, n over log n. So there you can get actually almost linear distance quantum error correcting codes. And the funny thing is, well, these ones here came from some sort of fancy number theory kind of stuff. But then all the other codes really are, in some sense, related to fiber bundles. Although, you know, the first one is really, it was explicitly kind of a bundle over something. But these later ones, they were sort of fiber bundles in disguise. Like, it was a fiber bundle, but the base space was not some manifold, but was actually some classical error correcting code. But there was this huge progress. And this talk is about kind of reversing this progress, meaning that this first error correcting code, that beat the square root n log n to the 1/4, it really came from a certain manifold. You know, they wrote down a very specific manifold. And this cellulation on this manifold gives us this code with these properties. The later ones, they're sort of inspired by topology, but there was no manifold involved. It was, like I said, it was a fiber bundle over a classical code. But the question is to try and reverse it and reverse engineer manifolds from those. So that's kind of the rapid fire introduction to error correcting codes. Now,
Matt,
yeah.
I know that 3/5 is your work. Is
Yeah.
the n of n also yours?
No, this is Pentelev and Kalichev, and that's appeared very soon after using construction. So yeah, so this is with Jungwon Han, Ryan O'Donnell. That one was Pentelev and Kalichev, and then there's a finer paper which is n to the 3/5 without the polylogs, but explicit, meaning no randomness involved in the construction. And that one's a very useful one to read for topologists because it sort of makes it clear how they're all instances of the same kind of fiber bundle thing with different choices of fiber and base space, even though like they're written rather differently. I don't have the references off the tip of my tongue, but if you look at my paper with Mike, which is the only paper under both our names that involves manifold in the title, these will all be referenced in there. So you'll have no trouble finding it if you look on archive. Okay, good. So now I want to talk about trying to, okay, how can we build a manifold from a code? Given a code, how can we define a manifold and some cellulation on the manifold that will give us back something with the properties inspired by the code? So one of the ingredients we're going to need is not just a quantum error correcting code, but a lift of a quantum error correcting code. And what does a lift mean? Well, we were given this chain complex C2 to C1 to C0 that was the error correcting code that is over F2. We want to lift it to some other chain complex. So these operators will be grad and grad prime. Let me draw this down a little bit further. Lift it to some other chain complex with some other operators that involve tildes over it, where we lift everything to the integers. Over Z. We want to lift everything to integers. So grad and grad prime should be matrices with entries in the integers rather than over F2. Matrix over Z. And if you take the entries mod 2, same as grad, grad. And similarly, if you look at grad prime tilde, if you take its entries mod 2, it should be the same as grad prime. So this is just a lift. It's, you take each 0 and it gets an even number, and each one becomes an odd number. Lifts always exist. That's not hard to show. But what we actually want is we want a sparse lift, meaning we want to preserve this kind of property. We want actually the sum of absolute values of entries in every row and column to be all of one still. And it's not clear that sparse lifts always exist. I think this is a really interesting open math question. Given a sparse chain complex over F2, does it necessarily have a sparse lift? My conjecture is no. I don't know a proof of that. I think they do not always have sparse lifts. However, all these codes I've mentioned do have sparse lifts. So the ingredient is a sparse lift. The reason we need this kind of ingredient, well, when we build the manifold, we're going to need signs present. We're going to need some +1 and -1 to tell us how to attach things with plus or minus signs. But one of the reasons we sort of should realize that we need it, yeah?
Sorry, can you repeat what sparse?
Sparse, sure. Every row and for every row and column of grad tilde and grad prime tilde, sum of absolute values of entries is O of 1. Is O of 1. So just, bounded by some constant. Yes?
Do you expect this correspondence between free manifolds and quantum error correcting codes to be functorial?
So functorial in the sense, like, what should it be respecting? Like, what kind of maps on the space of codes should we?
Is there going to be a way to think about operations on free manifolds corresponding to maps between different quantum error correcting codes? Is there going to be functor from category of free manifolds to chain complexes?
That's a really good question, and I don't know. I mean, there's certain operations that we think about with error correcting codes. Well, it's a good question. I'm not sure.
I think the natural operation is covered.
Okay.
So it's a covariant functor. The categories, manifolds, and homomorphisms are covering spaces. And then you can pull back cellulations under covariance and get generally codes with larger distance.
Okay. Yeah.
But just maps, continuous maps doesn't look good.
Okay. I was also wondering about products as another operation you might wonder about, because there's a natural product operation on codes. But the product our manifold has fixed dimensions, and the product would increase the dimension of the manifold, but our map is to a manifold of a given dimension regardless of what the input code is, so somehow you'd have to,
The map.
Yeah.
This sparse condition, is that the same thing as saying we want the code to be low weight?
Yes, but it's possible that the additional code was sparse, but the lift was not sparse. So you need to keep the lift sparse. One reason we're going to need it in the construction because we're going to need some signs to attach. But the other reason you should expect that we'll need it is that if you go back and look at just this picture, you realize that not only does the cellulation in the manifold give you a chain complex, as here, it actually gives you a chain complex over integers, because you can assign some you can say, well, the boundary of this 2-cell is not just the sum of those edges, but it's the sum of those edges with some particular orientation. And then the boundary of each edge will be not just the 2 vertices at its end, but it's plus 1 vertex minus the other vertex. So you get that, so it needs to exist. And one thing I should make clear, in case it wasn't clear, I've been writing the chain complex for the code as C2 to C1 to C0. And in this picture, I use 2 cells, 1 cells, and 0 cells. But if you give a cellulation of a manifold that's some higher dimensional manifold, not a 2-dimensional manifold, we could arbitrarily decide, okay, the 5 cells will be the checks, the 4 cells will be the qubits, and the 3 cells will be the other checks. And in fact, what we're going to construct is an 11 manifold where it's 5, 4, and 3. Okay, so the ingredient is this. What the construction gives is it gives a, input, so the input is a sparse lift. Input is a sparse lift. So the output will be an 11-dimensional manifold. Closed, no boundary. Pi1 is trivial. And it will give you also, Mike will correct me if I miss any of the conditions here. It will give you also a cellulation of that manifold. Cellulation of it. Oh, the manifold is, I think it can be chosen to be PL or smooth, as desired. Give you a cellulation of the manifold such that the number of 4 cells is actually the dimension of this C1, the number of qubits, times polylogs. So it's almost the number of qubits, you lose some polylogs. The chain complex that is a cellulation and a handle decomposition. The chain complex that is 5 handles to 4 handles by the attaching map to 3 handles will be isomorphic to C2 to C1, isomorphic to C2 to C1 to C0. Well, these lifted ones, I'm going to stop writing tildes throughout. The ingredient is a lift. I'm going to not write tildes. Everything from now on is referring to the lifted one. So this, you can just read off the error correcting code from the chain complex. You'll have a Riemannian metric on it, what we call an appropriately scaled Riemannian metric. And what does that mean? Meaning that the curvature is bounded. Curvature is O of 1, and the injectivity radius is omega of 1. So you haven't sort of done a cheat where like the size of a cell is basically of order 1. The geometry of the cells will be locally bounded in your cell decomposition, so each cell will have O of 1 other cells attached to it. Everything is kind of at the same scale. And some statements about the systoles, the weight of the systoles that I will tell you in a second when I refer to them, like the interest in geometry of this thing. So there's an additional property, which is the weight of the systoles that I'm going to mention now. So the output will be this 11 manifold from which you can read back off the code. Yeah?
So, just to make sure, so this lift, presumably for a given code, the lift is not unique, is that correct?
It's not unique, yes.
And so does that also mean that the manifold is potentially not unique?
Yeah, for a given input code, there may be different lifts, and so there may be, yeah, potentially different manifolds that give the same error correcting code. Yeah. Other questions? Okay. So one of the useful properties is that studies this is, so there's a term called a systole, and what is a p systole? A p systole is you look at something of dimension p. So if p is 1, it's just a line. P is 2, it's a surface. That's an element of p homology, and you look for a minimum weight one given this metric. So on a torus, a p-systole would be like a minimum length curve that goes all the way around the torus. A 1-systole would be that. And so a 4-systole is a minimum weight one that's dimension 4, and that corresponds to these qubits. A 7-systole is dual to it. And the minimum weight 4 systole will have a weight that is proportional to the x distance, and the minimum weight 7 systole will have a weight that is proportional to the z distance of the code. So the interesting thing about this then is there's this field of systolic geometry. You have this sort of surprising thing that you might have thought, okay, think about, just to give an example, imagine, say, a 3 torus of size L by L by L. And look at the minimum weight 1 systole will have weight 1. It's some like length 1 thing that goes around. The minimum weight 2 systole will be L squared, because it will be sort of L by L. And the product of those two is the volume. This one-dimensional thing times this two-dimensional thing gives you the volume. But there's this field of systolic geometry. People are interested in, like, can you have manifolds where these product of numbers are bigger? And here, essentially, it's as big as it could be. The 4 systole has weight that's almost the volume of the thing, appropriately scaled. That's the meaning of this, appropriately scaled, as does the 7 systole. So they're both sort of huge. And these are the so-called Z2 systoles. So this is the minimum weight. So these are not oriented things. So that's actually even harder to achieve this. So this achieves some property in systolic geometry that the original construction of this square root n log n to the 1/4 came from this field of systolic geometry and the existence of these these manifolds where you can get these high weight systoles. And here you show that you can use codes to reverse it and say that, okay, for the field of systolic geometry, here are some manifolds with extremely high weight systoles that come from the construction of error-correcting codes. So now let me just try and talk about how you do this building of manifolds from codes. So any questions up to here? More questions?
Just a quick question. So
Yeah.
I assume you guys tried low dimension does not work.
Yes, I'm good. Actually, when I explain, I'm going to show why we go up to 7. Yeah, I'm about to explain that. Another question?
I missed the definition of P in P systole.
Yeah, so P systole is a minimum weight. So it's a, I'll just be a little loose about exactly what I say, but it's like a p-dimensional object that you're looking at the minimum weight thing that is a representative of H sub t, P homology. That's the P systole. So
Why were you focusing on 4 and 7?
so 4 and 7 is because, like I said, I have right here, the four-dimensional things will be the qubits. And so the 4 systole will correspond to the qubits. And so just like in the toric code example I was giving, the one-dimensional objects were the qubits, and then the one-dimensional thing, this line going around the torus, was like a chain of x or z errors. So here we're looking at a 4-dimensional object, and that's the errors. And then the co-systole, you want to look at like the dual dimension. And the sort of 3, 4, and 5 are the same as C0, C1, and C2. And then the dual dimensions 6, 7, and 8. This is an 11 manifold, so the dual dimensions 6, 7, and 8 will be reversed from that. So it'll be like the co-systole. Yes?
When you say like four handles, do you mean elements of H4 of this 11 manifold?
We're going to give a handle decomposition of the manifold, and that's what I mean by 4 handles. Yeah, and I'll try and explain what a handle decomposition is too. I'm going to, in this, probably like half the audience knows and half the, yeah.
So you mentioned that the lifting is non-trivial. You expect it non-trivial.
Yeah.
That you, for all the codes used to have a them, they're all lifted.
So yeah, and essentially the reason is that all these, at least the fiber bundle type codes all have this lift. And the reason is that those codes are almost, like a classical error correcting code trivially has a lift because you just lift 0 to 0 and 1 to 1, this naive lift. And there's no, if you tried to do that on a chain complex for a quantum error correcting code, you might not obey the condition that grad prime is 0. But on a classical error correcting code, it's trivial to lift. And those codes are almost built out of products. They're built out of twisted products. And so you can just do the naive lift on each one, and then taking the product tells you the sign, and you can just use the same sign in the twisted product. It's almost a product of two complexes, which introduces a minus sign when you lift, and you just need that minus sign. Okay. So how would you reverse engineer a code from a manifold? Sorry, a manifold from a code. So what you might try and do is you might try to, so I'm going to start out by building something that's not a manifold. Even in this naive attempt, we're not going to build something that's a manifold. We're going to build something that's like very singular. It's going to be made out of a bunch of cells joined together. It's going to have a boundary. And we'll try and solve all those problems later. So it might look like, a bunch of triangles glued together in certain ways. And if you could do that, then maybe you could thicken it and get rid of the boundary in some way. But let's just deal with those issues later. So your first try might be 0 cells are X checks. You might try that. 1 cell is a qubit. So that worked, that was the example I drew above, previously for the toric code. The trouble is that a 1 cell has only 2 0 cells in its boundary. So that means that each qubit can participate in only 2 checks. So each qubit in only 2 checks. And that's no good because most of the codes we have don't have that. Each qubit participates in O of 1, but more than 2 checks. So no good. We can throw that out. So let's try to go a dimension higher. So let's say, okay, maybe 1 cells are X checks. Now you've noticed that I just put cells in quotes. The reason is, what is a cell? A cell really should be something that's like a ball. So it should be like a line, like this. But instead, we're going to have something that's one-dimensional, but might not just be a line. It might be some other one-dimensional thing. And similarly, we'll put 2 cells in quotes and so on. So you might say, okay, for every X check, I'm going to draw circles. Now, here, I'm going to mention something sort of like, you might have tried to do this. You might have said, okay, for every X check, there's a circle, and we're going to glue them all together at a point. This will be our starting of our construction. We'll just have like 1 cell per check. And then we're going to go glue on some 2 cells for the qubits in some way to make the boundary right. But this is no good because all checks meet at a point. And that is not going to be good for getting our desired bounded geometry. At this point, right here, the number of cells coming in is diverging. It's diverging with the size of the code, and that's going to make it hard to put our nice bounded geometry and bounded cellulation on. So let's throw that out. Instead, let's try to make them what we'll call free floating. So what we'll start with is for every check, we'll have a cell like that. So let me give an example of what we might try to do. Here is a very simple code. Let's say we have 2 qubits, and 2 X checks. And the X checks will be both on the 2 qubits, X1, X2, X1, X2. I know it's the same check twice, but pretend it's 2 checks. So I just wrote 2 circles, 1 for each check. So now a qubit, so then the 2 cells should be qubits. So I'm going to need two cells, and each 2 cell needs to attach to these 2 checks because each of the checks involves both qubits. So qubit 1 is some 2-dimensional thing, and it needs to attach to both checks, and qubit 2 is some 2-dimensional thing. So what you want to draw is a, say, S2, a sphere, S2, punctured by 2 disks, and then those 2 punctures will attach to these 2 circles. And then the other qubit will also be corresponding to some sphere with 2 punctures, and those will also attach to those 2 circles. And what you see that you will have built is you'll have, taken these 2 checks, and you will have joined them by qubit in some way like that, and then you'll join them again by the other qubit going around, and back like that. And that will give you a torus by doing this. What you've just constructed is a torus. You've taken a torus, and you've taken the torus, and you've made it, it's decomposed as 2 cylinders. Each of the qubits will correspond to a cylinder, and you've glued 2 cylinders together at their ends, and you've gotten a torus. This is not really good either for a couple reasons. These things aren't cells. These qubits aren't cells. They're cylinders, which are not balls. And very closely related, we've introduced some extra homology. This code should have some, what does this code have? It has one logical bit. It's a 2, 1. We've imposed that the x's are the same, and okay, the d is actually 1 in this case because it has no protection against one kind of error. It has one logical bit, So it should have some second homology. Its second homology should be 1 because qubits are 2 cells, and that's correct. And it has a redundancy among the checks. The 2 checks are redundant with each other. So the input chain complex has some 0th homology. So the output should have first Betty number equal to 1. The output thing should have just 1 redundancy. But instead, the torus has first Betty number equal to 2. We've generated spurious homology by this construction. And this is very closely related to the fact that, so B1 is 2, not 1, even though the input chain complex had a redundancy of 1 among the checks. So again, this does not quite work. So, okay. So we proceed a little bit higher. What we might try to say is, okay, let's make the 3 cells. Yes?
If it was the same X check, why did you want to put it in twice?
Yeah, that's a good question. Why did you want to put it in twice? I mean, of course, you might try to just delete it. And there is always, you can certainly, from the point of view of then K and D, you can always delete redundant checks among the X ones. Now, many of the interesting codes have redundancies among the checks. The toric code has no local redundancy among the checks. There's no product of a small number of checks that's redundant, but the product of all the X checks is redundant, so it has some, you could call it non-local redundancy among the checks. But yeah, you might say it's not such a serious issue, but the trouble is that then that spurious first homology, when you go to the next step of if there were some Z checks, which there weren't in this case, could turn that into some spurious second homology. And that spurious second homology would mean that you've sort of added some extra logical qubit and you wouldn't have a control over its distance. And then all those systolic results would be messed up. And at another level of what you say, well, some of this might not be the most parsimonious construction. We're going up to an 11 manifold, and probably it can be reduced a little bit. But, you know, just let's be, you know, give us all the room we need as long as it's some fixed dimension. And then probably the final dimension can be reduced, especially for some of those input codes. So what you might try is making the 3 cells into qubits, then the 2 quote cells into qubits. The 2 cells might be X checks, and the 4 cells might be Z checks. In this case, we might imagine taking, here's another funny code, X1, X2, Z1, Z2, Z1, Z2. Yes, I've been very redundant about writing checks. If I work this example out right, and I might have this one wrong here because I was just trying to look back through my notes and remember one of the examples where you run into trouble, and I think this is one, but I might have it wrong. After you do the first step of saying, okay, so for each of those 2 checks, X1, X2, and the other X1, X2, I'm going to have some S2 somewhere. And then for each of the 2 qubits, what I need to have is in S3 with 2 punctures, and then I'll glue those 2 punctures onto the 2 checks. I think what you get is you get like an S2 cross S1, and then when you glue on the Z checks, so that's after forming this manifold, this sort of cell complex from the Q and the X. After gluing on the Z checks, what you wind up getting is you wind up getting some spurious that's Q and X. And then after you glue on the Z checks, what you wind up getting is you get spurious third homology. So you still get some spurious homology, spurious H3 when you glue on those. So our final thing is to make 4 cells into qubits. And this turns out to work. So if you take 4 cells into qubits, the prescription then is something like the following. You start with, for every X check, you have some S3, which is kind of free floating. They're not attached to each other. You then, for every qubit, you have some 4 cell, which has some punctures in it. You then glue that into the X checks, and then you, there is a consistent way that I won't get into to then, given your sparse lift as input, and it's really important that you know the signs from the lift, you have a way to glue in the 5 cells. Thus far, what I've talked about is cells. So also, like a cell, So a 2-cell might be just like a little triangle like that. But the trouble is then, maybe you've made something that looks like very singular. It might have some like 3 triangles meeting at a point or something like this. So what you can do is you can resolve those singularities by thickening things a bit. So instead of attaching cells, you attach handles. So all these handles then become objects that are 11-dimensional objects, and you attach them in a particular way. And this gives you an 11-dimensional manifold with a boundary. Then you attach it to a copy of its dual, and in that way you kill the boundary. This is the rough outline of the reverse engineering procedure. You just glue things in, and yeah.
So, sorry, is the claim that, for any code,
Yes.
that I might hand you that I'm interested in, for cells,
The claim is that for any code, if you can find a sparse lift of it, which we can do for a lot of the example codes, although I conjecture you can't always do it, then we can write down a manifold so that 4 cells correspond to qubits, 3 cells correspond to x checks, 5 cells correspond to z checks. And that will basically read back off your original code. And in the process, we'll have done a few extra things that will increase the total number of cells by a polylog factor. But basically, the total number of cells will just be the number of qubits in your code up to a polylog. That's the claim.
How does the dimension, so here you talk about 11 dimensions?
Yes, this will be an 11-dimensional manifold. That's because we have qubits, we have x, q, and z corresponding to 3, 4, and 5. And we did that to get out of these problems that were arising with spurious homology. And then that gives us some sort of singular 5-dimensional thing with a boundary. And in order to resolve those, we work in just more than twice the dimension, so 11 dimensions.
I have a question for Mike over more than 4. So this is using that 5 complex embedded into 11 dimensions for 3, right?
Did you say bicomplex?
The 11 comes from the embedding of a 5 complex into 11 dimensions.
Yeah, you can think that way. That's a good way to think about it.
I wonder if you can reduce one more dimension.
Yeah, you probably, with some work, can get down to 9. I mean, I think actually math is pretty tough, and I was really starting to remember how this worked during the lecture. But I think the real point is this free-floating idea, which Matt introduced to remove the initial problem of congestion at a vertex. Because the way a topologist would normally build spaces is just like going after a cell complex, where you start with the point and everything attaches to the previous stuff. And actually, it was Matt's idea to do this free-floating stuff. It never would have occurred to me because I'm raised as a topologist. I always want to attach things to the point. But it's very creative not to do that, But the whole price of free-floating is you get this extra homology that Matt was talking about, this spurious homology. And then the point of going up to a high dimension like 11 is just to create a buffer from the low-dimensional nonsense that's created by avoiding point attachment. That's the spurious stuff. You just want to put the spurious homology in a different set of dimensions than the encoding topology. So you have to, that's why you need room. So the spurious stuff is like 1, 2, 3, and 3, 4, 5 is where the code is.
Yeah, exactly. Yeah, I mean, I agree with that. And probably, and this gets back to the question from, this 11 is, and 11 is probably more than you need, especially if, maybe it's okay if you have spurious third homology because you only maybe care about the 4th systole, so maybe it's okay. So maybe you can do it in a lower dimension. Probably the dimensions can be reduced, yeah. Probably the dimensions can be reduced. So let me I'll just mention a few more things about this construction. So, and like some open problems and aspects of this construction. So, kind of a goal is can you make M just S4 cross S7? Can you do that? So what this construction gives is the input is a code and the output is a manifold. So in reality, the input is a family of codes, with growing number of qubits and with distances growing in a particular fashion. And the output is a family of manifolds with this particular growing systoles. However, you realize that this output family of manifolds, it's not the same manifold with different metrics on it. It's different manifolds that you're producing. Whereas in a lot of the systolic literature, they're interested in here's a fixed manifold, can we put different metrics on it to exhibit the systolic freedom? And one immediate way you realize that you've constructed different manifolds is that these codes that come from this construction, the number of logical qubits k that they encode is changing with n. And in the coding literature, this is perceived as a virtue because this is called the rate of the code. And the bigger k is, the better the code is. But this k is increasing with n, which means that the fourth Betti number of this manifold is increasing with n. The fourth Betti number of the corresponding manifold is increasing with n. So you might like to ask, can we actually do it on a fixed manifold? So we try to get there. So let me sort of mention some of the things we do in an attempt to get there. And can you make M S4 cross S7 and still have this systolic freedom? So one of the first questions is then, can you kill all but one logical qubit? Meaning, can you take the error correcting code and make k equals 1? In that way, then the resulting manifold would have fourth Betti number equal to 1. So at least it has a chance of being a fixed manifold. This is something a coding theorist would never want to do, but you know, so this is a question for coding theory, and we don't know how to do that. Outside of this, you know, that's a question about the input code. You can ask, well, what about our construction? Does our construction have any other features that tell us that it can't just be S4 cross S7, other than just this fourth homology? So first, what is pi1? A nice thing is that we can, as I said, we can guarantee that pi1 is trivial from this construction. And this comes from a particular result. It actually turns out if you just follow the construction I give, there will likely be some non-trivial pi1. You know, for example, in the toy constructions I was getting like S1 cross S1 and then S2 cross S1. And maybe when we go up, we wind up getting like S3 cross S1 or something. But there is this leftover pi1 in the construction. However, you can kill pi1. You can kill pi1 at a polylogarithmic cost. Polylogarithmic cost in the number of cells. And this is a consequence of a resulting in graph theory, just a purely graph theoretic statement. This follows from a statement that given any graph G, you might want to ask, can you come up with a basis of cycles that will kill pi1? And the answer is there exists a so-called weakly fundamental. You can look up what that means, fundamental cycle basis. So this will be a basis that kills pi1. So these will be some basis of cycles so that if you attach a disk to every one of these cycles, that will kill pi1 of the graph. Such that every edge appears at most polylog times. At most polylog of the number of vertices times. So this is just purely a combinatoric result that you can do this given any graph. You can find this. So what is the meaning of this graph? Well, an interesting thing is that if there is a cycle basis where every edge appears twice, this means the graph is planar. You know, you just draw the graph in a plane, and then the cycles are the obvious ones. It's just the little cycles that go around the cells. And then every edge appears in two of them. But you can actually, so you can always do it where each edge appears in most polylog many times. So then you take your manifold, you find these cycles that exist, and then you just glue on some 2 cells to kill those. And this has a polylog increase. And it's important that each edge appears in most polylog times so you don't really congest. No edge has an enormous number of cells attaching to it. So that way you can kill pi1. You can kill second homology and third homology also by attaching some stuff. It's not clear from the construction whether or not, but you're left with some question. Really, the main question you're left with is, can you change the input code to kill all the fourth homology? And so this is an open problem. Like, can you make M S4 cross S7? I think one of the main things is, can you kill all but one logical qubit of the code? And if you can do that, well, I have to check our paper, but I think then you're almost all the way there to making M just a fixed cellulation, a fixed manifold, and a fixed cellulation on it. So, yeah.
I'm a little bit confused about how you're constructing this manifold from the code. So you want the 4 handles, or well, I guess you picked dimension 4 for the handle. And how are you incorporating the data of the delta?
Right. So delta tells you the attaching map. So it tells you this 4 handle gets attached to these 3 handles. And then the condition that it's a chain complex gives you some consistency condition that you can attach the 5 handles to the 4 handles in an appropriate way. So just delta is literally, at a naive level, delta is just saying, glue this one onto this one. The lift is telling you that that can be done in a consistent way. Yeah.
And I have another question. Why do we want M to equal S4 cross S7?
Well, I guess, like I said, it would be nice to have M just be a fixed thing. I mean, I guess maybe Mike can answer this, but I think it's getting into like the culture of systolic geometry. I guess it originated from looking at a fixed manifold and considering a family of metrics on that fixed manifold. And then showing that, there are fixed manifolds. There are fixed manifolds where you can give a family of metrics on that manifold so that there is so-called systolic freedom. The product of, say, the 1 systole times the 2 systole diverges compared to the volume, the 3-dimensional volume of this manifold. If it's a 3 manifold, for example, this is possible. There's also cases of systolic rigidity, like on a torus. There's a best metric you can put. There's a best you can achieve with a metric. There's some bound that the product of the 1 systole times, well, the 1 systole squared is at most the area times some constant that you can't do better than a certain amount. So I guess it originated as a question about metrics on a first fixed manifold. We would be sort of almost as happy if it weren't S4 cross S7, but rather like some other fixed manifold. Maybe if you didn't make it 1 logical qubit, but 2 logical qubits, then, maybe you'd be almost as happy. But that would just be like most striking. I remember Mike saying to me that he thought it would be great also if we could prove systolic freedom on S4 cross S7, because if you just told a systolic geometry person that you had, systolic freedom on S4 cross S7 with the Z2 systolic freedom and almost linear, they would be assuming that it came from like, a hot vibration and like the octonians or something like that. They would, never guess that it came from this. Yeah, John.
How does your graph theoretic statement go along with the appropriately scaled metric?
Yeah, so the graph theoretic statement, so the important thing is it's only polylog time, so what winds up, you violate things like a polylog amount, but that's okay, you can then just thicken it by like a poly. So each of these 1 cells winds up having like polylog many 2 cells attached to it maybe, so then if you make the 1 cell like polylog thicker, you could attach them each at a slightly different height onto it. And then you can keep your metric appropriately scaled. So, yeah. Yeah, I finished a little early, but take more questions or.
So you use CSS code. Does it also work for other code?
Yeah, I mean there are other additive quantum codes where there is some kind of chain complex interpretation, but it's not as strong. I mean, it's a good question. There may be something that can be done. I mean, certainly certainly let me point out that there's a nice result that given any quantum code that's just a stabilizer quantum code, but the stabilizers are not CSS type, so they might be like, X1, Y3, Z7, or something like that. Given any such code, there is a CSS quantum code that achieves almost the same parameters. That is, the N, the K, and the D are all changed by constant amounts. So you obtain the same scaling of D with N.
How about the weight?
It's also still LDPC code too. And again, the weight, maybe the weight doubles or something, but it's still, all the parameters just change by a constant amount. The construction is, this is like, I think Bravi, Terhall, and maybe, I don't remember if there are other co-authors on there. The construction is, first you take your non-CSS code, you represent every qubit by 4 Majoranas subject to a constraint. You write your checks of your non-CSS code as quadratics in the Majoranas. Then you observe that the commutativity implies that you've written down some self-dual vector space. And then you just take that self-dual vector space and promote it back to a CSS code where every one of those checks becomes both an X check and a Z check. And so the number of qubits increase, because what you do is you turn the qubit into 4 Majoranas, and then you turn Majoranas back into qubits, but everything changed by constant factor. So I think the weight of the checks maybe doubles because every check becomes a 2. I think the weight of the checks doubles, the number of qubits multiplies by 4. But otherwise.
So you said stabilizer, so that means all the level 1 model can be turned into...
No, sorry, stabilizer meaning Pauli, like is product of X, Y, and Z, yeah.
So it's not like a level 1.
Yeah. And you can do the same construction for like Q-trick codes as an input or something, because we just care about a lift in the end. But if your input is a Q-trick code and you prove something about the distance as a Q-trick code, probably it then tells you something about the Z3 systolic freedom instead of Z2 systolic freedom.
Does this map preserve only the NKT parameters up to some constant, or it also preserves like the properties of the excitations in the...
Yeah, I mean, you really get basically the chain complex you read off from the code is basically the output, the input chain complex, so everything is preserved. Actually, that reminds me of one thing I did want to mention before I stop talking. I think there's probably, in terms of open problems, I think there's a lot of codes that can give rise to really interesting manifolds. So there are NKD codes, which are quantum, where it's n theta of n and theta of square root n. These are called hypergraph product codes. Hypergraph product codes. So these are codes where the number of the number of logical qubits is proportional to the total number of qubits. The distance is only square root, but they encode an enormous amount of information. So these then give manifolds where B4 is proportional to the volume of the manifold. And the distance is square root n. And I think this is kind of interesting because there was the first time there was a manifold constructed where a certain Betty number was proportional to the volume, and you had the distance is growing faster than log. These came from hyperbolic manifolds. So if you take a hyperbolic two-dimensional manifold, you can get what you can get is you can get k theta of n, and that just comes from Gauss-Bonnet, and you can get d log n. So that isn't that big a distance. And if you take a hyperbolic 4 manifold, what you can get is you get k as theta of n when you put the qubits in dimension 2, and you can get d that's, I don't know, into like 0.01 or something. It's something that's a little bit super logarithmic at some power, but it's some very low power. So here what you can do is you can build some manifold with an extensive Betty number and with large distance. So it's an interesting property of a manifold. And there are classical codes where there is n theta of n, theta of n. And so then these correspond to some manifolds. And you don't need to go anywhere near up to dimension 11 if you're just trying to reproduce a classical chain complex. You get up to like 5 or 7 or something, some fairly low dimensional classical manifolds where you don't have a bound on both systole and cosystole, but you have a bound on the systole, and you also have this extensive homology. So there's sort of like a whole family of interesting things that can come from codes that give rise to maybe surprising things in manifolds. Yeah.
In the very beginning, you mentioned there's a Riemannian metric in the story.
Yeah.
You said there's a totally scaled Riemannian metric.
Yes.
So can you say where did it come from?
You want to answer?
Well, it just comes from smoothing out the handle decomposition. I mean, we build the handle decomposition in some locally finite way. And then the attaching maps are all smooth, so you can patch together a Riemannian metric. It would be extremely uninteresting and difficult to write down the metric locally. But the point is, just because the attaching maps are not congested, you know that the curvatures don't blow up. That's all we observe. But actually, look, I wanted to make a comment for condensed matter physicists, make them more comfortable with the idea of systolic freedom. It has an amazingly beautiful application in work that Chet and I and a lot of his students participated in studying maybe 6-7 years ago, up till very recently, under the name perfect metal. So if you look this up, what Chet and his collaborators did is they constructed interacting 1D electron systems, so on a wire, with many channels. And the number of channels has to do with the dimension of very interesting lattices. So like 23 left movers and right movers, something like that. You have the kind of one of the versions of a Leach lattice, the odd Leach lattice in the game. And the idea is that in this formalism, you think of a real vector space spanned by these channels, and the possible perturbations are lattice points in this vector space. And whether the perturbation is relevant or irrelevant has to do with the length of the vector, the lattice vector. And it was kind of conventional wisdom in condensed matter for decades. You couldn't make these interacting electron systems stable to all perturbations. You couldn't make them all irrelevant at low temperature. Because the feeling was, just like Nat indicated, if you take a torus, you start with the square torus, if you stretch it out to a rectangle, well, you're doing one good thing, you're making one direction irrelevant, making that direction long, but the other direction becomes short, it appears. So if you don't think too much about lattices and you just know about rectangular lattices, then it looks like it's a losing battle. There'll always be some relatively short directions. The people who know about high-dimensional lattices know that this isn't right. Like the E8 lattice and the Leach lattice, they have the property that the shortest vectors are getting longer and longer as you go up in dimension. And that's in fact generic. So what Chet and his friends did is they engineered the interactions to produce all the operators at the vertices of these nice lattices which don't have any short vectors. So you kind of have your cake and eat it too. You don't have like duality between decreasing relevance in one direction and increasing in another. You kind of win in all directions. So that's a very high dimensional manifold that comes up, much higher than ours. But it's not in sort of physical space. It's in this sort of abstract space associated with the channels.
Sorry, I was just wondering, do you have an example where all of the manifolds that you make are actually homeomorphic? Like, it's a sequence of manifolds, right?
Yeah, so if the input code is this HHO, PK, BE, whatever, any of these codes that really beat the square root n, we know that the output manifolds are not homeomorphic. I mean, they just have different fourth Betty numbers, so it's immediate. It's a good question. I mean, probably, I think so. I think if you probably input, I don't know, probably if you just input the toric code, they're all going to have, there will be. But, I'd have to check through and make sure because, there's a bunch of obstructions and do the fourth Betty numbers differ? And I think we can, in that case, cancel all the extra homology, and at least there's no obvious obstruction. Yeah, I'm not sure, and that's certainly something we should be able to answer before trying to get this grand goal. I mean, it's somewhat funny that the input is this completely benign sequence of cellulations of the same manifold, and then the output is, we're not quite sure it's the same one or not.
Well, if there are no more questions, why don't we thank Matt?